Okay, this is Chapter 7. We're going to be talking about linear momentum, and we're also going to be talking about collisions. And what you're seeing on the front slide here is going to be a collision occurring between two billiard balls. We have the cue ball, and then we have the 11 ball. And while I'm on this slide, I'm going to just point out the notation that's going to be used in this chapter. Here we're going to have the mass and velocity of the billiard ball beforehand. Over here we're going to have the mass and the velocity of the billiard ball right here, and we're going to have the mass and velocity of the 11 ball. Notice that there is a prime right here on each of these. In this chapter, your book uses the prime to denote after the collision has occurred. Over here we have no prime, so this is going to denote the velocity of the ball before a collision occurs. So in this chapter we're going to define what is momentum and how that's related to force. Very important concept of conservation of momentum. How momentum is related to force is going to be something called impulse, and we're going to talk about how all that's related to collisions of billiard balls. Very, very, very important concept, conservation of energy and conservation of momentum in collisions. We're going to talk about two types of collisions and how the conservation of energy and conservation of momentum play roles in each of these types of collisions. One of which is going to be an elastic collision. The other definition is going to be for inelastic collisions. We're going to talk very briefly about collisions in 2 or 3 dimensions. Definition of center of mass, how that relates, and the center of mass for the human body, and how the center of mass is related to translational motion, are all of the equations for kinematics that we're already very familiar with. So let's start by defining what is momentum. Momentum is going to be this symbol P here, and it's going to be related to an object's mass and the object's velocity, keeping in mind that the object's velocity is also a vector quantity. Therefore, momentum is a vector quantity. What that means is it has both a magnitude and a direction. If an object's velocity is 5 meters per second to the east and it has a mass of 1, then its momentum is going to be 5 kilogram meters per second to the east. So it's going to have a direction associated with that. If you define east to be in this direction and that direction to be positive, then the momentum will also be positive. If it's traveling in that direction and you want to call that direction negative, then the momentum will also be negative. I talked very briefly about the units here of momentum. We know that the unit of mass is going to be a kilogram. We know that the unit of velocity is going to be meters per second. So the unit that you would expect to see for momentum is going to be a kilogram meter per second. So objects that are moving, they have momentum, and suppose we want to change that momentum. Suppose we want to change their velocity. You know that to do that you need to apply a force. And it turns out that you can start with Newton's second law, right? Sum of forces is equal to mass times acceleration. And if you follow section 7.1 of the book, you can see how they talk about the change in acceleration being the velocity, or the acceleration being the change in velocity, and the sum of forces is going to be equal to the change in momentum. So let's think about how we can relate this to our everyday life. You know that your truck or your car is going to have some momentum associated with it. Suppose you have your car and a bicycle, and they're both traveling at the same velocity, same direction. Obviously, you kind of intuitively know that your car is going to have much more momentum than the bicycle is. The reason for that is because the car has a lot more mass. Similarly, in order to stop your car, in order to change the momentum all the way down to 0, it's going to take a lot more force to stop a car traveling the same velocity as a bicycle than compared to the amount of force it would take to stop a bicycle. So why even bother talking about momentum at all? We already know everything we need from kinematics. Well, it turns out that if we consider collisions, this thing that I defined on the last page, this thing called momentum, is actually going to be conserved. What that means is the total amount of momentum in an isolated system is going to be a constant. When I say isolated system, I mean no external forces, no friction, no wind, nothing like that. We can write this simply by saying that the momentum before a collision must be equal to the momentum after a collision. And this, as I said, this is going to be a constant value. Let's take a look at my system here, which is actually going to be two trains. Here I have to say the momentum before is going to be related to the mass of train car A multiplied by the velocity of train car A. It's going to be the momentum of train car A plus the mass of car B multiplied by the velocity of car B. Add these two guys together and I get my momentum beforehand. So mass of A, velocity of A, plus mass of B, velocity of B. That is the momentum of my system before the collision occurs. That must be the momentum after the collision occurs. So mass of A, velocity of A prime, mass of B, velocity of B prime. And in this particular collision, velocity of A and velocity of B are going to be the same because they stick together. The book's calling that V. I'll do that in just a second. I want to write the most general case possible first. So mass of A, velocity of A prime, plus mass of B, velocity B prime. This equation would apply if these two guys did not stick together. As they are in this case, we know that velocity A prime is going to be equal to velocity of B prime, and I'm going to call that a single velocity, velocity prime, keeping in mind that, remember on the first slide I said that the prime is indicating that it is after a collision has occurred. In this particular case, it's going to be mass of A plus mass of B, velocity prime. Clean this guy up just a hair. There we go. For this particular case, we can say, well, let's take a look at velocity B. Initially, I know that this guy is going to be equal to 0, and I know the masses of the trains. This is example 7.3, and I know mass of A, I know mass of B, I know the velocity of A. What I'm really interested in is what is this V prime. So I can isolate that guy to say that V prime is going to be equal to the mass of A velocity of A divided by the mass of A plus the mass of B. And here I know that the masses of these trains are going to be 10,000 kilograms each, so I can simply go ahead and plug that in. So 10,000 kilograms multiplied by 24 meters per second. Mass of A is 10,000, and then mass of B is going to be also 10,000. Go ahead and punch that into your calculator, and we come up with a final velocity of 12 meters per second. Intuitively, that makes sense because initially we were going 24 meters per second. We know that it has to be smaller, and since the masses of these two guys are going to be equal, intuitively you kind of say, okay, well, the velocity should be cut in half. The last thing I want to point out is the velocity, it comes out to be a positive number right here. Here what I did was I defined the velocity of A to be in the positive x direction here, and the numbers would work out to be negative if for some reason the train would end up going in that direction, which you'll see when you work out problems for example, elastic collisions, where one of the trains bounces off of the other one and it has a velocity in the negative direction. The negative, again, is simply going to indicate the direction of the velocity. A very neat way we can apply the conservation of momentum is to think about how a rocket works. If we consider the rocket and the gas to be one system, and initially it's at rest, we can write down what its momentum is going to be. It's going to be 0. So we would say before something happens, we're going to have some momentum, and afterwards we're going to have some gas going in the backwards direction and the rocket going in the positive direction. We're going to have the momentum afterwards. The momentum beforehand, I've already said, is going to be the mass of the rocket plus the gas multiplied by its velocity. Afterwards, we have the momentum of the gas plus the momentum of the rocket. If I set this guy equal to 0 here, all I have is 0 must be equal to the momentum of the gas plus the momentum of the rocket. And what that tells me is the momentum of the gas must be equal to the negative momentum of the rocket, or the mass of the gas multiplied by the velocity of the gas is going to be negative the mass of the rocket multiplied by the velocity of the rocket. As I said on the last slide, this negative sign here means that the gas and rocket are going in opposite directions, and you can see that pictorially right here. It's actually very hard to account for the mass of the rocket constantly changing. It becomes a very complicated problem, but looking at it simply as an example of conservation of momentum, it's very simple to write this down. Something else that we know is the mass of the gas is quite small. The mass of the rocket here is going to be quite large. What this says is the velocity of the gas must be very, 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 very large in order to produce even a small velocity of the rocket. Let's take a look at what actually happens during the collision moment itself. We know in order to change an object's momentum, we're going to have to apply a force, and we're going to apply that force for some amount of time. If we take this equation from the previous slide and we rewrite it such that we multiply both sides by delta t, then we can say that the force multiplied by the time you applied that force for must be equal to the change in momentum. And the book defines this to be a special quantity, which is called the impulse, which is a force multiplied by a change in time. Note that this is also equal to the change in momentum. So we really have two ways to go about calculating the impulse. We can calculate it knowing the force and the amount of time that's involved, or we can go about and calculate it to be the change in momentum. For example, in the case of this ball right here, if I happen to know the mass and velocity of the ball entering the tennis racket, and I know the mass and velocity of the ball leaving the tennis racket, and due to high-speed video I know how long it was in contact for the ball, what I can do is I can solve for my impulse using the change in momentum. That's going to be a number. What I can then do is say, I know that it was applied for a certain amount of time. I can go ahead and I can solve for how much force this tennis racket applied to the ball. Just another look at it, where if I look at the impulse being the change in momentum, again being a force over some change in time, if you think about that, the momentum of a system is not something you're going to have a whole lot of control over in a collision. It's going to be equal to the masses and velocities of the objects that are involved. What you might be able to control is this change in time, or how long the forces were acting for. What this is saying is, if you have a very, very, very fast collision, so this delta t is going to be very, very, very small, then correspondingly this force must be very large. If we're talking about something like a car or a dumpster dive as in Mythbusters, then that can be a bad thing. You don't want to have you don't want to have large forces applied to your car or your body. However, if the collision can be lengthened, so this delta time is going to be very large, then what that means is correspondingly these forces are going to be relatively small for the same type of collision where this change in momentum is simply going to be a number, the mass multiplied by the velocity. For your car, it has something called crumple zones, where what's going on is the engine will drop out of the compartment and the front end will fold up like an accordion. What that is doing is that is making this delta t, this time in which forces are acting on your car, to be larger. That's making the forces on your body to be smaller. Similarly, if you think about your steering wheel and why we have airbags, that's doing the same thing. It is trying to increase the amount of time that your head would be slowing down, trying to make the forces on your body, on your head, to be as small as possible. In reality, if we look at the force over some time, it's going to be more like this graph right here, or a force that is varying over time. as you can imagine, that can be quite messy. But for the purposes of this class, we can say that the time of a collision is going to be very short, so we don't need to worry about the exact time dependence of the force. We can use an average force. What we can do, and you can prove this mathematically, and in my calculus-based class they will, the area of this green shaded region is going to be equal to this area right here, only now rather than having some widely varying force, I'm looking at the average force. So I can say that the change in momentum is going to be equal to the average force multiplied by the change in time, at least for this particular class.